Thank you, Mark. Thank you all for being here. It's great to be back in Paris. It's always good to be back in Paris, and even better to be back in your new building, which I haven't seen before. So thank you for being here, and although it is being recorded, please interrupt, to those of you who know me well, if I say something too quickly or whatever, please say, and we'll see where we go. What I want to do, and this is partly informed by, we had a 2-day meeting of the Royal Society last week on plate tectonics and how it might have developed on Earth, because Earth remains the only planet at the moment that we know of where plate tectonics is active, so why is that? And the second issue is, what can you get from geology that will tell you when plate tectonics may start? And how can we take that forward together? So that's what the bit I want to focus on. And let's start with the kind of things we might think about in that context. So here is someone's favorite model for the kind of computer modeling you can do in geodynamics to see what might be going on underneath fairly rigid plates. And some of the points we might like to keep in mind are, firstly, this issue about recognizing subduction in the geological record is, I think, not the same as recognizing plate tectonics. All right, so locally we may have stuff going down into the Earth, and they may give you signals that look like subduction, but developing an Earth that has sustainable plate tectonics that will keep going is a different issue. So to keep subduction and plate tectonics kind of a bit separate in our minds may be helpful. We can see, maybe, from the geological record, when we get plates, when we get lumps of geology where there is sufficient rigidity that we might wish to call them plates. All right? So when the lithosphere, when the crust and record becomes rigid enough, you might want to call it a plate, is something we could look for. We clearly, historically, with paleomag, we've been able to look for lateral movement. We can go in the field and identify compressional tectonics. And finally, maybe we could come back to rates of crustal growth. Hidden in here is this issue of upscaling in geology, which is tremendously difficult. I can go to my favorite part of West Greenland and persuade you subduction took place at 3.8 billion years ago on that piece of real estate, on that piece of ground. But does that mean subduction was all over the Earth? Does that mean plate tectonics was active? How do we do the upscaling for the significance of this one detailed case study into some global model? And one of the ways we can try and do it is to contrast the results from local detailed case studies with more global data sets of what we could look at. And if we believe that crudely that maybe the rates of generation of continental crust haven't changed that much through time, then maybe seeing when the rates of crustal growth really reduced, because then we were destroying crust, because then we had subduction and plate tectonics, might be a way of linking the case study to some global model that we might sign up to. So it's not to say that's the right way to do it or the wrong way to do it, it's just to indicate how we might address this issue about upscaling. So in the talk, what I'd like to do is look a little bit at distribution of ages. This is the geological record that we have. What does it look like? Always in geology, we have cycles, we have global cycles. What do they tell us? Then to go into regional, local case studies where we can look at tectonics, metamorphic grade, seismic anisotropy, and geochemistry. What do they tell us locally? And then can we pull out of that to bigger scale issues, like does the composition of new continental crust change through time, and what might that link to? What other changes take place at 3 billion years? And are those changes enough to say that maybe then we were really developing plate tectonics in a way quite similar to what we know it today? But I thought I'd start with a story. Clearly, dating zircons has been how we've unraveled the timescale of deep time, of when different processes, different events took place in the geological record. And remember, every time you date a zircon, effectively you're dating a granite. So there are hundreds of thousands of zircon ages available to look at. And one of the things we do is we use hafnium isotopes in zircon to look at whether things derive from the crust or the mantle. And Oxford recently have been celebrating the life of a chemist called Harry Moseley, who was killed in Gallipoli in 1915, aged 27. But he was the person who suggested that the periodic table should be based on atomic number, not atomic weight. And in doing that, he had 4 holes in his table, which no one knew what the elements were. One of them happened to be hafnium, and hafnium was then in turn isolated from the mineral zircon, which is what we use all the time, in the 1920s in Copenhagen. And from memory, the name hafnium comes from the Latin name for Copenhagen, where people were studying it. So it's just to link up. We used zircons all the time for dating. It had a story as part of recognizing a new way to look at a periodic table, identifying elements that wasn't there. One of them was hafnium, we use all the time, and it comes from zircon, and we're still doing that all these many years later. I was warned not to show many isotope diagrams, so this is almost it. Here is a data compilation just along age on the bottom, so this is 4.5 billion years through to the present day. This is from a compilation a few years ago. This then is age on the bottom, and this is hafnium isotope ratios. And basically the data sets are the same, so this is histograms of these data. And the hafnium isotope ratios are such that if it's at 0, it's roughly maybe the bulk Earth. And if it was positive up at 20, it might be the mantle, and down here it's all crustal. And what's strange initially is that these are hundreds of thousands of zircon analyses, hundreds of thousands of making granite, of magmatic events. And what is unexpected in our steady state Earth, all right, is that there are peaks of ages. These are just these peaks and troughs, and peaks and troughs are simply these peaks and troughs and peaks and troughs of crystallization ages when you plot them all up. And these are global data sets, and we have to infer that these are global peaks and troughs of data sets. We can come back to why that might be, but it's just to highlight it's an unexpected, if you like, record of the evolution of the continental crust that we have these peaks and troughs of ages, and that they're global data sets and they're presumably global signals. In sharp contrast, if you look at this axis, this is in a sense a single data set with no peaks and troughs in terms of hafnium isotope ratios. But what's interesting about it is that very few of these hafnium isotope ratios plot up here where the mantle plots, where new crust would plot. So it's not a surprise geologically, but most zircons come from granite. Most granite comes from pre-existing crustal rocks. And we've known since Hutton in the 1780s that in a way most rocks in the geological record were derived from previous rocks. This is a miserable record to go and find out how the crust was made if most of the samples you have came from rocks that were already in the crust. I want to put another way, this is a hugely expensive way to show that Hutton was maybe right all those millions of years, hundreds of years ago, but they come together in that kind of way. But the main take-home message here is peaks and troughs of ages. Why might they be? What can we say about them? And if we take exactly the same kind of data set, this is 100,000 zircon ages, also in a histogram, just showing that these peaks and troughs of ages are also mirrored by ages of high-pressure granulite facies metamorphic rocks. So these are from Mike Brown. This is a thermal gradient up the side, so you've got relatively high temperature going down to relatively high pressure granulite facies metamorphism, and these are their ages. And their ages, too, cluster with the zircon ages, for the most part, implying that if this is a primary record, right, we had pulses of making granite, and we had pulses of making high-grade metamorphism. Or perhaps it's not a primary record, and we have to think of other interpretations. But it also highlights that in terms of thermal gradient, you can still read stuff off this, even if you're worrying about the distribution of ages. The gradients are interesting, and the fact that these higher pressure rocks really date mostly from 700 million years or so ago, is when people would now agree that sort of cold subduction had started, and we were looking at subduction similar to that we see at the present day, even though we're still making granulites under different conditions. But these peaks of ages are still there, both in zircons, therefore in granites, and also in granulites. And what intrigued us a few years ago then was, should we not think not only about making magma, but about preserving it, about retaining it in the crust, in our crustal record? And if you go, this is not our work, but Scholl and Van Hunen and various others have said that if you look at mass balance along the western US and South America, what is really striking is that you subduct sedimentary material at very similar rates to that at which you make magmas. So the rate at which you make magma in all these wonderful, spectacular volcanoes of the Andes and of the western US is roughly the same as the rate at which you destroy crust. So this, in a sense, is a miserable place to make long-term continental crust. You're getting rid of it as fast as you make it. In contrast, of course, that when you have collision, if you take the Alps and the Himalayas, you obviously trap in the last stages of subduction and then whatever you've formed after collision in terms of thermal evolution of the orogenic system and the making of leucogranites and whatever. And material is much more readily trapped in the crust here in terms of collision than it is trapped in the crust here in terms of active subduction. So this led us to this rather old now thought experiment, which simply, with no axes, this is time along the bottom from a subduction phase to a collision phase to an extension phase. If you think of the volumes of magma generated during subduction, they're in the blue curve, so they're huge, all those volcanoes. Then as you go into collision phase, you get less and less of the subduction, a little bit of magma generated post-collision, and then you have breakup. But in contrast, as we've just seen, the chance of preserving these magmas, i.e. here in red, depending whether you have an advancing or retreating arc system, are really very low. So you have all this magma poorly preserved. When you make collision, you preserve stuff more and more. And then as you break up, you don't make many zircons anyway, and the record is hard to establish. But it suggests that you will end up with a peak of ages which is the balance between the rates at which magma is generated and the rates at which it's likely to survive in and around the collision phase. All right? So this is a way of making peaks of magma in and around the collision phase, which may or may not link to the development of supercontinents. The implication, of course, is that these peaks of ages are a bias of the geological record, and that they're not pulses of sort of upheaval in the mantle to make more granite here and less granite here, that there is secondary phenomenon as to how that looks. So if we just think about some tests for that, up in the top right is the diagram we've seen already. So this is just granulites and zircons, but what I didn't highlight enough before is the peaks of ages and the peaks of metamorphic ages preserved match up with these gray bars, which are the ages of supercontinents. Now, supercontinents are a bit negotiable. Some people believe in old ones more than others. They're hard to tie down, perhaps. But I think two things stand out. One is that we know quite a lot about the Grenville event. And the Grenville event was in here at about 1 billion years or so ago. Gave you lots of zircons preserved, but it was not a time of making lots of new crust. So in a sense, we know the geology of the Grenville. It was a time of reworking pre-existing crust. It was much less a time of making new crust. So we have a sense of what went on here. And secondly, you can take various indices of crustal reworking. And the most neutral one is probably, this is oxygen isotopes in zircons from Chris Spencer, with a running mean through oxygen isotopes in zircons, highlighting that there are peaks and troughs in the amount of reworked material trapped in the zircons that are the record that we've been looking at. And those peaks in terms of more crustal reworking tend to be at the times of the supercontinents, They tend to be at the times of the peaks of ages seen in the zircon record. So that would imply, again, that these are times, presumably, of crustal thickening, of collision, when there's more chance of reworking pre-existing crust than there is before and after. So the two strands of evidence that say these peaks of ages are due to times of increased collision, as in perhaps the making of supercontinents. One is our understanding of the geology of the Grenville, and the other is that if you take indices of reworking, those degrees of crustal reworking are greater at the times of the peaks of ages at the times of supercontinents. So we would say they were secondary items, and we would put them together in this kind of summary diagram down on the bottom right. So ignore the smooth curves for a second. This then is data that you've seen. This is the histogram. Naught is over here, the present day, 4.5 through to here. These are the peaks of ages. Here are the supercontinents. Those are the ones that we think have matched up. So it leaves us with a sense that the continental record since 3 billion and the first supercontinent, so-called, has been biased by the development of those supercontinents to give us these peaks of ages. It follows, if you're worrying about crustal growth, all right, that supercontinents become times of increased crustal growth, not because you made more crust, but because more of the crust you made you kept, all right? So you can still have models in which these peaks of crystallization ages are also times of crustal growth, as we'll see in a moment. As I say, not because you made more crust, but because more of the crust that you made, you kept in the crust. What then about these crustal growth curves? Obviously, what we're trying to do is to get a sense of when and how the continental crust was generated through time, and that's what these various curves are plotted in green and red. They are all anchored at 100% being the present volume of the continental crust, and their various estimates back through time. Some you can see date from here, Oleg and Rousseau in the 1980s. But in a way, we have been very slow as a subject to get our heads around them. All these things were called crustal evolution models. Everyone thought that's what they were. But the two in green, right, are crustal evolution models based on the present-day distribution of rocks of different model ages. So those are model ages are simply when material was derived from the mantle. And all the discussion in Oleg and Rousseau and so on was whether we could agree what the present-day distribution of rocks of different model ages might be, and to call that a crustal growth curve. But if we draw back and think about that for a second, right, it seems to me very unlikely that the proportion of, let's say, Phanerozoic rocks to Archean rocks preserved at the present day should tell us anything, really, about the amount of crust that was generated in the Archean. So this notion, right, that we should somehow be anchored to the present-day distribution of geological ages or model ages as a true record of balance between Archean and younger crust seems, I think, at best misplaced. And what the other models have tried to do, all right, here in red, either with zircons and Belousova and Dweem, or with argon from Bernard Marty's group, was to use other data sets that tried to model the volumes of continental crust that were there at 3 billion, irrespective of how much is retained today. So that's a whole step change in our understanding of these crustal growth curves and what they might mean. And we can look at how they work a little bit, but clearly they all imply typically that by 3 billion years, I don't know, 60 to 70% of the present volume of the crust might have been generated, and you can then develop models saying that was what was generated, this is what's left today, and that amount's been destroyed by subduction. But it is this issue about there are different growth curves designed in different ways and with different implications, and perhaps we've been slow in articulating. Green is model ages as presently preserved, red are volumes of crust generated through time, for different other arguments. So let's pause there and see what rocks tell us. We know much of the geology of the Archean is different from rocks we look at today. This is from McGregor as president of the Geological Society of South Africa in the 1950s, all right, when Zimbabwe was Southern Rhodesia, at least to the Brits. Has this wonderful quote here about the central part of the colony. But the key point is that he was making the point that this outcrop pattern of Southern Rhodesia of Zimbabwe is different from what we see in linear belts today. It's different from what we see in orogenesis today. It's marked by low grades of metamorphism and by these basin and swell granitic bodies with greenstone belts and stuff trapped in the negative areas in between. So we've known for a long time these areas are different. And we can look a little bit more. That hasn't worked entirely well. But let me see if I can reconstruct it. We can look at a little bit more in terms of tectonic styles in Western Australia. Because the aspect that we can surely get from the geological record is when the crust became reasonably rigid. All right? And here, this is a map of the Pilbara. So this is northwest Australia, with again these domal granitic features and these negative areas of basin areas of greenstone belts and sediments in between. These are of quite a big area. You can make vertical tectonic structures in collision zones like the Alps, but if you take a map of the Alps, which might form domes afterwards, it's about a sixth of the area of the Pilbara. So this is a much bigger area of dome and basin structures than you would get out of today's collision zones. So that is what happened pre about 3.1 billion years. Secondly, then, if you go down further south in Western Australia, here's Perth, so this is the Yilgarn Craton. Up in the top corner here, it's hard to see, but it's quite similar to this, and it's older. But then, in the late Archean, you get these north-northwest belts that you may just be able to pick out as eastern Yilgarn became accreted in a series of belts against the older Craton. So by the late Archean, you were getting linear features, much more like things that you might have linked to plate margins. And then, of course, by 2.4, you have this big dike swarm. So by 2.4, you know, right, that this terrain was rigid enough to retain a record of dike swarms in a way that we don't see much before that. So we go in time from 3.1, dome and basin structure, late Archean, 2.8, 2.9, these more linear belts, north-northwest through here, and then by 2.5, 2.4, the whole thing is rigid enough to have dike swarms. So we're beginning to trace a little bit that history. Oh, well, that's where they've been. We don't need all that again. The second part, then, is metamorphic conditions. So here's a PT plot. Here is a common description of these low-grade rocks that McGregor talked about in the Pilbara and the Barberton. Pressures less than 5 kilobars, temperatures, depending how close you are to a granite, can 500 degrees and less, but relatively low grade. So this is the map of the Pilbara again with the dome and basin structure. Here's a map of the Alps, which might have domal basin structures in a relatively restricted area compared to this. It seems to me, as a non-metamorphic petrologist, we often get seduced by these pressure-temperature timelines, which of course all end up at low grade. But at one level, it's not clear that's the right question. The question surely is much more that in isostatic equilibrium, what will be the dominant metamorphic grade on the surface? Here, in isostatic equilibrium, the dominant grade is here. If you've had collision zones deeply eroded, the dominant grade on the surface is here, and it would depend on your model for the Swiss Alps as how you think it will evolve and how hot you think it will get. So the metamorphic record in isostatic equilibrium on the surface in collision zones that might give you some domes is much higher grade than, again, you see in the Pilbara and the Barberton. Seismic anisotropy, I will just mention in passing, but in essence, from seismic anisotropy, in principle, you can evaluate whether there are fabrics in, let's say, the top 200 kilometers of the lithosphere that you're looking at. And these are data from silver from southern Africa. Here is the Cap Val Craton, here's Zimbabwe up here, here's the Limpopo belt going through. And these lines are sense of fabrics. But what is intriguing is that when you go to the Cap Val, and to areas out to the west, when you go to the Cap Val that has the dome and basin structure, you don't see this fabric through the lithosphere. So there is a chance, again, you can map out the transition from dome and basin structure vertical tectonics into more lateral tectonics, also using seismic anisotropy and how that comes about. And finally, 2 seconds on geochemistry. If you simply look at what people have concluded, all right, in looking at the geochemistry of different rocks of ages from 3.8 to 2.6, this is simply a summary of their conclusions, right? So I'm just, for the sake of this argument, taking all their conclusions are robust, okay? It's not our job to say that thorium-niobium ratio is not as robust, or it is robust, or whatever. But if we just take the data that they've published, 2 interesting things come out. One is that from 3.8 to 2.5, there are parts of the world where subduction-related magma suites, bonanites, high thorium-niobium rocks have been identified in Eastern Superior and West Greenland, and also later on in the Pilbara. And there are areas through the same period of time where no subduction signal has been seen, where it's dominated by within plate. A geologist's response would be both things have been going on through this period of time, all right? And it's not clear to me that would be a surprise. But you can take it one step further, and that is that these rocks here, Zimbabwe, we've seen Pilbara, Barberton, with an intraplate signal, all have this vertical dome and basin type tectonics. So there is a matchup between this intraplate and this vertical tectonics. When you go back to older rocks, here is the fabric in East Superior of these rocks. The trouble is this fabric is late Archean, it's 2.8, 2.9. These rocks are 3.8. We don't have fabrics to go with the rocks. We don't have fabrics to go with the chemistry when we get to that strongly developed linear fabrics. But in many areas, these strong fabrics are actually late Archean, and in many cases they follow this more vertical tectonic setting. So just to bring it all together, and this was put together by Peter Kaywood recently, what can we say from the geological record? So this is time up the side, 3.2 up to 2.4, and these are just different cratonic areas from Superior to Cap Val all the way across. In green then is just ages of TTG. So these are sodic TTG granites. Many Archean terrains sort of culminate, if you like, in the development of potassic and more periluminous granites. And various people have argued this, and this is just bringing their data together. But you can see in different places, these TTG culminate in the development of potassic granites. Sometimes it's older, as in the Pilbara, sometimes it's younger. But each of these records of TTG culminates in potassic granite. Why does it matter? It matters because those are reworking pre-existing crust, which may mean you have to have lithosphere strong enough to thicken in order to melt it to give you the potassic granites. Different places in different times in different places. And then also in yellow, you see the onset of more compressional tectonics and the development of more linear fabrics or planar fabrics as you look them on maps. Again, taking place at the end of the TTG cycle in different times. And then at the very end, you see the ages of these dike swarms, which are all 2.6 billion years and later. All right? So that by here, you've got dike swarms, you've got brittle enough, strong enough geology to hold on to them. As you come through here, it's at the end of these cycles that you get presumably crustal thickening to get your potassic granites, compressional tectonics, and you moved away from vertical tectonics to compressional tectonics at different places, as we've seen here and elsewhere. So maybe that's as good as we can do in terms of case studies from geology. And let me then switch back a gear for the last few minutes or so and change scales. Because one of the reasons we've argued is that's what you can do in case studies. You can see that different things happen at different times in different places. How do you bring them together on a bigger scale? And one of the things that we tried to do was to look at the composition of new continental crust. So here, this is an orogenic system from Namibia, with the sediments and granites that you're stuck with on the surface. Here's an old section of the continental crust, sediments and granites at the surface we get to sample. But can we get back to what the green material is, what the new magma adding to the crust is in the generation of new continental crust? And this was a way just to try and do that. And what we did in the Dwee et al. Paper in 2015 was to look at rubidium-strontium ratios as inferred from neodymium and strontium isotopes. And how we get it, in a sense, matters less, but it's initially just to highlight that if you take big data sets, rubidium-strontium ratios increase quite consistently with silica, at least until you get to very high silica rocks. And of course, RBSR ratios you can get from strontium isotopes, and if you have a simple model whereby here's the present day, here's 4 billion years, if you sample a rock at the present day, you calculate its initial ratio. One has a high initial ratio, one has a low initial ratio, and you know the model neodymium age, you can calculate the rubidium-strontium ratio of the source of this granite, between the model neodymium age when it was derived from the mantle and the formation of the magma in your hand. So that gives you the rubidium-strontium ratio of the source of the magma in your hand, which is by definition from the model age, the composition in terms of RBSR when it was derived from the mantle. The rubidium-strontium ratio of new crust, which links to the silica content of new crust. And this was one of those things that, worked in a sense very much better than it might have done. So here was just trawling 13,000 rocks from the literature where there was good ages, strontium and neodymium isotope ratios. So you can calculate the rubidium-strontium ratio at the time when the new crust was formed. So this is the rubidium-strontium ratio in that early stage at the time of the model age. So here's the new crust formation age, model age 4.5 through to 0 at the present day. And here's the RBSR ratio in effect of new crust in this most simple way to express our discussion. Clearly, in the Archean, this is very messy. But if we allow ourselves to be taken by the maximum probability curve, what is striking is that through to about 3 billion years, this rubidium-strontium ratio is effectively the same as the mantle. So making new crust early on didn't deplete the mantle in rubidium-strontium ratio. Okay? And more than that, if you believe the correlation between RBSR and silica, then your new crust was mafic. It had whatever, less than 50% silica, the kind of stuff you see in greenstone belts. But what was unexpected is that from 3 billion years, the rubidium-strontium ratio estimated for this new crustal material gradually increased. So you've changed the way in which you've made new continental crust from mafic material to stuff of more and more intermediate composition. And this is clearly the stuff we get in subduction zones. This is not stuff linked to subduction easily. So there's a change in the composition of the continental crust. And you can take it one step further because then it links back to geology if this link is plausible. And here is data today from Central South America, a rubidium-strontium ratio of magmas near the surface against crustal thickness. And you can see how the rubidium-strontium ratio of magmas is sensitive to the thickness of the continental crust at the time and place the magma was generated. And again, it's not a surprise. Thick magma needs more differentiation to get the magma through. You get higher RBSR ratios and higher silica. And presumably when it gets thick enough to remelt, you have this step up to even higher RBSR and higher silica magmas. So this is plausible and geologically comprehensible. And if you want to translate this thickness from RBSR into this thickness and take it back to the data we've just looked at, here then becomes the thickness of the continental crust at the site at which you made new crust, varying from below 20 kilometers or so through to about 3 billion years, and then increasing in crustal thickness because the RBSR of the new crust increases up to about 40 kilometers or so before it decreases. So that is a chance to put the RBSR ratio of new crust, the silica content of new crust, to the crustal thickness that was there at the time you made the new crust, as you change from mafic material before 3 billion into more intermediate stuff as the crust thickened thereafter. So let's try and bring that together and do two aspects. Here then is just a plot of age, 4 billion years through to the present day. This is the percent of material in crustal reworking. And in a way, the details are a bit less important, but they're things that you've seen before. So here are the histograms of zircons that you've seen before, matching up with times of supercontinents, and at least matching up with times of increased crustal reworking. If you look at oxygen in zircons, in magmas through time, they start to increase at about 3 billion years, again, because your lithosphere regime is rigid enough and thickened enough to start to remobilize stuff within the crust. If you take the reworking axes we've seen, they change with these peaks of ages, as we've seen there. And the green curve shows that thickness change from below 20 kilometers up to 3 billion years to gradual change at 3 billion. We've seen potassic granites sort of come in around 3 billion. We've seen dike swarms get going by 2.6. So it seems there's a lot going on, all right, that highlight a change in our understanding of the record of the continental crust and the lithosphere we had around at about 3 billion years. And let's just take that to the final issue, which is then rates of reworking. This then is just a guide, really. And these are the percent continental crust, 100% of the present day, 4.5 billion years through to 0 at the present. Here is the age profile of just geological ages in the geological record. Most of the rocks we see are young. Here is the Condé and Astor distribution of model ages at the present day, presently preserved, so that's the record. And then here is the Dweem et al. Zircon curve, which is very similar to Belucifer's. And all these curves are based on, all right, is anchoring yourself at 100% of the present volume of the crust, and then for different time slices, just evaluating the proportion of material that in this time slice that is new continental crust from that is reworking older continental crust. So these curves are simply the ratio between new crust to rework crust in different times through Earth history. They're no more sophisticated than that, all right? But they have the advantage, all right, that they're not anchored on anything at the present day except 100% of the present day surface. And so that's how these curves have developed. And clearly, these kind of curves with Belucifer and the Argon curve and various trace element curves imply 70% crust at 3 billion, which implies there's a kink, which implies there's a change in the rate at which you make new continental crust. So if we put all those together, and just to summarize that, here's a number of the other things that go on at 3 billion. Same plot, volume of crust. Here's the Dweem curve. Here are the shale curves that Oleg and Russo would have used with different erosion factors. But these shale curves are calculated the same way as the zircon curve, just as the proportion of new and reworked crust in every time slice, not in the way that they did it. Here's the Bernard Marty's group argon curve, all of them highlighting that by 3 billion years, 60 to 80% of the continental crust was already formed in terms of volume. And the other things that go on at that time are, Shari and Richardson highlighted that if you look at it, inclusions in diamonds, 3 billion years is the onset of when you start to get eclogite inclusions in diamonds, implying that basalt has been taken back down into the earth and trapped as diamonds. You have a reduction in the MgO content in the upper crust, according to Tang et al. We've seen the change in RBSR. We've not looked today, but there's increased seismic anisotropy as these strong fabrics getting. But critically, we have this reduction in crustal growth rates from a rapid growth to 3 billion to a slackening off in growth thereafter. And if we accept that this is unlikely to be a sharp change in the rate at which we made new crust, then this is most simply interpreted as an increase in the rate at which we destroy crust, because subduction's taken over and plate tectonics has become the key way at which new continental crust is made. So in summary, and this is an little sketch from Steve Foley. Here's the curve we've just seen. We've seen links between vertical tectonics and within plate magma types in terms of the earlier part of the Archean record that we understand. We've seen that there may well be a regional distribution of subduction-related magmas in the Archean. Maybe there was local subduction, transient subduction going on. We've seen a little bit of strong regional deformation fabrics by the end of the Archean. But the key thing is to put the case studies in a more global context is the change in RBSR ratio of the new crust at 3 billion and the change in the rate of crustal growth, because then we're destroying more crust. We haven't touched on it, but the same sort of argument would be that if you're thinking about this is pre-3 billion, here you're stabilizing your lithosphere, you're making it strong enough to thicken it, to have dike swarms preserved from about 3 billion onwards. And the low iron peridotites that are important to the buoyancy in many Archean areas are best modeled as generated at really shallow levels where there were ridges and swept it underneath. So that implies that by 3 billion years there were ridges, all right? There were shallow areas where these cratonic peridotites could be made. There was lateral forces to bring them in and stabilize them underneath the continental areas. So I hope it gives you some sense, really, of how we can ever think about putting case studies in the context of global models, and whether if we put those two things together, I can persuade you there may well have been some subduction before 3 billion, but perhaps around 3 billion is the time where plate tectonics became the dominant process on the planet that we live in. Thanks very much.
This is quick. Okay, so time is open for questions and comments. Who wants to ask the first question? Yes, John.
You're saying that around 3 billion years ago, subduction took over and it started destroying crust. But maybe I'm a bit naive. Doesn't subduction destroy oceanic lithosphere and the oceanic crust, and the continental crust remains relatively intact?
Okay. This is yes to the oceanic crust, but remember, go back to that the data from the Andes and the Western US, right? That subduction is taking down continental material at about the same rate as we're generating it, all right? So the load of continental sediment, and maybe with some tectonic erosion, that's going down, let's say, beneath the Andes, is as high as the volume of magma you're making every year, all right? So subduction is used here to do both. And the difficulty is, of course, we can't constrain the oceanic one well, because we don't have any. Okay, but we do see this change in the rate of crustal growth. Okay, and it's interesting if you think back to the Armstrong models. Those of you who've been in this game a long time, who argued in the 80s, right, that actually the Earth was hot. We made the present volume of the continental crust way back at 4 billion years, and he did it because he believed plate tectonics would then destroy it. All right, and so the argument has been almost since then that once plate tectonics gets going, that it's quite efficient, as we see today off the end, is in destroying continental crust as fast as we can make it.
You're making the point that the way you destroy continental crust is by subducting sediments.
Yep.
But you could argue also that a lot of destruction of continental crust is made in collision zones, because not only will you reduce the volume by eroding the higher topography part of it, but also you will reduce the area occupied by the continent because you're shortening the continent. So one interpretation of your curve could be that after about 3 billion years, you had sufficiently large continents that they would run into collisions with one another, and thereby favoring destruction.
Yep. No, I mean, it's absolutely fair that we don't model well what, if you like, what happens to material caught up in, let's say, the Himalayas, all right? And in essence, whether a significant part of that, let me back off another step. I mean, the other step is, of course, that you have to have a way of trapping subduction-related magmas to make the bulk composition of the crust, okay? And if we're not doing that well in active subduction zones because preservation is poor, we clearly have to trap it in some way in collision zones in this model. But my sense of collision zones that yes, they make high mountains and yes, they erode. And then it's a question of what happens to that material before it goes back to the oceans and how long that residence time is before it goes back to the oceans and gets destroyed from my crust, if you like, all right? And if that time is quite long, all right, then that allows my model to work. But I don't know that we model it very well. Yeah.
What do you think about the possible anthropogenic impact on the global crust volume and such effects if the human being can live more than 1,000 years or 1 million years?
Yeah, I don't think that I have data of a long enough time period to comment. It's also a particular institute which has strong views in some areas on it. But yeah, I mean, at the moment, I don't think I have data where we can usefully address that. Would it surprise me? Not necessarily, but I think it's going to be time before we can get the data.
When we're looking at Archean cratons today, these are the ones that have the largest or the thickest lithospheric keel, whereas in this simple, the schematic here, it doesn't seem to be the case. So does the growth of the lithosphere occur concurrently with the crust, or is it two separate processes?
This often comes down to geologic prejudice. And I mean, mine is that it's mostly concurrent, all right? But, I mean, it's very hard to get magmatic records apart from 1 or 2 diamonds out of the mantle lithosphere that's older than 3 billion. Okay, all right? So that crudely fits with this. And if you wanted to sweep in low iron peridotites from underneath hot shallow ridges, that would say that early on there was some crust floating around where you tacked in 3 billion year old lithosphere. And I couldn't, it seems to me that's quite likely, all right? But it's really hard to test, yeah? But after that, if you have orogenic systems, you quite often see similar ages in the stuff in the mantle lithosphere. But it's tricky, and it's a little bit down to geological prejudice of the person who's answering the question.
Some science fiction, so you talk only about Earth. What about other planets? And do you think your model would apply in other part of the universe?
Well, we've no evidence that it is at the moment, right? Well, I think the thing that I find it hard to get my head around, right, and we're talking with Institut people here a little bit, is that if you talk to many modelers, they will say, if you tell me the starting composition and conditions of your planet, we'll tell you how it behaves. And one of the difficulties is how we put that, which is presumably quite a major element statement, and maybe a volatile statement, into bed with the Earth comes from ensortyte chondrites, or particular things that are about isotopes and sometimes trace element ratios. All right, and I think at the moment we don't make that link very well. All right, so I don't think that I have any way here to predict how it would go. The difficulty is that we really need, from studies on Venus and other areas where you've got great maps about tectonic processes, that we need our stagnant lid geodynamic models in 3D so we get maps we can compare. And of course that's the difficulty, yeah? But if we had maps that we could generate in geodynamic processes and compare to what's left of the record of the early Earth and to Venus and so on, maybe we could make some progress. But at the moment, I'm too ignorant to do more than that. He's coming behind you.
What I'm getting here is that you are linking plate tectonics, subduction processes.
Yep.
What about the ridges? If they were there to form the ocean, the question was earlier that you have to have oceanic lithosphere to subduct.
Yeah.
So there was already, one of the processes is the spreading center happening somewhere in the middle of ocean. So tectonic process was happening prior to the subduction.
Yeah, but I think this is a little bit about how we're handling our models from stagnant or single lid Earth planets, right? And as I understand it, those models can certainly have material that comes up, and therefore some material goes down, and so you can get signals that might be subduction linked, even though it's not happening the way we're doing it. If you just were to believe our crustal model, all right, and it says 70%...
Continental crustal model.
Yeah, it is. No, absolutely. But it says 70% of the crust by 3 billion, 20 kilometers thick. That's the same area as the crust today, all right? And since then, it only got thicker, all right? So we would have to say, not very good evidence, right, that we had similar areas of oceans that we have today at 3 billion, if our very Mickey Mouse calculation was right. And then those ridges, yeah, would have to be there when we have no record, yeah? I mean, or the only record we have are those mantle peridotite where people want to make them under hot, shallow ridges, which is tenuous.
Okay. More questions? Claude.
You don't mention a lot the superior province, but I think it makes a very good case for your basic model.
Yeah.
Because it's made of the craton core is clearly made of crust that's I can see that from the standpoint of hydro measurements. It's depleted in radioactive elements, so it has to be more mafic.
Yeah.
And the belts that were credited to it at starting about 2.8 billion years are definitely made of more radiogenic material, more evolved granitic stuff.
Yeah.
And there's clearly a difference between this older crust and the newer crust, but there's also a clear difference between the deformation fabrics in the core and in the belts. So the superior province, I think, is a good case study.
No, thank you. I mean, we had looked a bit at the deformation fabrics, and I had taken them out for lack of time. And obviously, working with Mike Kendall, that's the stuff he knew about. But I was less familiar with the composition of new crust. But no, I agree. Mike Kendall was relieved, I think, to identify that many of these fabrics that we see are really quite late Archean, because otherwise that would have been a confusion in his model about how that lithosphere developed in the superior province.
Is it possible to link the plate tectonics with the growth of the inner core? It's very...
Not by me, but I'm sure by some, right? Are there suggestions here? Yeah. Not by me, I'm afraid. You think the timing is similar? Yeah, okay. Well, coincidence is a step, yeah.
Okay, so no further question. Maybe the last one. Okay.
Chris, you are talking more about the onset of plate tectonic, but how about the mechanism? So
right.
What's the mechanism for the initialization of the plate tectonic?
Okay, I mean, in a sense, the discussion seems to be in two parts, right? There seem to be lots of ways of triggering subduction, right? That you can have collisions, you can have extraterrestrial stuff, and so on. But the people who were in discussions really just last week said that for plate tectonics to be sustainable, you had to have already developed enough deformation fabric, all right, that zones of weakness would have been clear, all right? Now, I'm not quite sure how you get those going unless we're better at doing the geodynamics of the late stage before plate tectonics, all right? Okay. But at the moment, the necessary precondition, which isn't quite an answer to the question you asked, seems to me to have zones of weakness developed, which can be then reactivated on things that then become plate margins, all right? All the arguments become, provided you have a mechanism of taking your plate down to eclogite facies, then you can drive it the same way as you drive it today with the density of the plate going down. And then it's a question of what the tip over is, that enough material is going down to eclogite facies to drag more material after it. So I think it's close, okay, and just a question of whether you can satisfy those conditions. And I infer that you can without knowing exactly what the tip over was at the time.
Okay, so discussion can go on in the Mediatek. Let's thank the speaker once again.